Homework 2.2, more on functions, video 7. Homework due Friday, May 22nd, 2020 at 11:59 p.m. In the previous video, we discussed how to analyze a function to see if its graph would have y-axis symmetry or origin symmetry. And in the midst of that, we defined two types of functions. One was called an even function, one was called an odd function. There's a reason the adjectives even and odd are chosen here. Hopefully I'll allude to that as we go through these examples. But an even function, f of negative x equals f of x, or equivalently, opposite inputs yield equal outputs. For odd functions, f of negative x equals negative f of x, or equivalently, opposite inputs yield opposite outputs. It's worth mentioning that most functions are neither even nor odd. I don't want to say it's a very unique characteristic, but more often than not, you're neither. So if we happen to run across an even or an odd function, we can take advantage of the fact that its graph has a certain symmetry. An even function's graph has y-axis symmetry, whereas an odd function's graph has origin symmetry. So for these examples, which are similar to questions 9 through 14 on your homework 2.2, we have three functions and we're going to analyze them to see if they're even, odd, or neither, and then state any symmetries as a consequence of being even or odd. So let's start with A. f of x equals x to the third power minus 4x. In order to check to see if a function is even or odd, both of these criteria start with the same thing on the left. They both start with f of negative x. And then we compare it to see if we get the original function or the opposite of the original function. So the first thing we need to do is put a negative in and see what happens. Okay, we can do that by changing all the x's to parentheses and leaving everything else alone. So parentheses to the third power minus 4 times parentheses, and then fill in those parentheses with a negative x. And now, like we did when we were checking for symmetries of equations graphs, we need to ask ourselves what happens to all the negatives. Let's start with the negative x to the third power. That means negative x times negative x times negative x. I know that x times x times x is going to make x to the third power, but what's going to happen to all three negatives? Well, when you multiply three negatives, does it come out negative or positive? The first two negatives make it positive, but the third one swoops back in and changes it back to negative. So multiplying three negatives will result in a negative. What about over here? Well, negative times negative is positive, and 4 times x is just 4x. So the consequence of substituting a negative x into the function is we get negative x to the third power plus 4x. But now the second thing we have to do is compare. We have to compare to the original function and compare to the opposite of the original function. So these are our steps. Evaluate f of negative x, and then compare it to the original versus the opposite of the original. Comparing it to the original is easy. Either this looks like it started or it didn't. This one doesn't. The result of inserting a negative x into the function is not the same as just inserting an x into the function. So we can instantly see that f of negative x is not equal to f of x. This is not equal to that. They have the same pieces, but the signs aren't the same. So we know that this function is not even. That was the criteria for being an even function. But we also have to compare it to the negative of the function. So what does the negative of the function look like? Well, it's actually not that hard if you remember that this negative applies to the entire function. In other words, to find negative of the function, we have to find the negative of x to the third minus 4x. Well, this invokes a real quick distributive property. Distribute the negative to each half. The x cubed becomes negative, but the minus 4x becomes positive. Wait a second, this looks familiar. This is the same as that. In other words, putting a negative into the function gives us the same answer as gives us the opposite of answer of putting in a negative x. In other words, f of negative x equals negative f of x. I think I said that last part wrong. Let me try it again. In other words, putting in a negative gives the opposite of putting in a positive. This is equal to that. That's the definition of being an odd function. So this first function is odd. That's dd. Looks like a bunch of O's. Let's try lowercase d's. The first function is odd. And as a consequence, that means that the graph has origin symmetry. By the way, the reason odd functions are called odd is if you have a polynomial function, which means just a bunch of powers of x's, not that, but this is a polynomial and this is a polynomial. If you have a polynomial function and all of the powers are odd, power of 3 implied power of 1, then your function is odd. So I just gave you a real quick way to look at a polynomial and go, you're odd. All of the powers on the x's are odd. Guess why an even function is called even? Because if you're a polynomial function and all of your powers are even, then the function is even. So what do you think this one is? One of its powers is 2, the other implied power is 1. Are all of the powers odd? No. So it's probably not an odd function. It's not. Are all of the powers even? No. So it's probably not an even function. It's not. But when you get functions that aren't polynomials, that rule doesn't necessarily apply. So we can't just look at this one and say all the powers are even, therefore the function is even. In fact, I'm going to go back and change this one real quick. I'm just going to change this to a 2x, not an x squared. Because now the powers are a mixture of even and odd, but this function is either even or odd, and we'll find out in a minute. But let's get back to b, g of x equals x squared plus x. If we want to check to see if this function is even or odd, the first thing we need to do is see what happens when we put in a negative x, because both of the criteria start with, let's stick in a negative x. So if we put in a negative x into the function, then we just go over here, change each x to parentheses, and then fill them in with a negative x, and then see what happens. The square will turn the negative positive, so the first term goes back to being an x squared. But the second term, positive times negative is negative, we end up getting x squared minus x. So the second thing we have to do is compare. And again, we're comparing to the original function and the opposite of the original function. Comparing to the original function is easy. Either it matches or it doesn't. There are some exceptions where you do a little bit of sleight of hand, but let's not worry about that right now. Yours are going to be pretty transparent. In this case, putting in a negative is not the same as putting in a positive. So in other words, when we put in a negative, we got this, but it's not equal to putting in a positive x. So this is also not even. But what about odd? Will the first result be the opposite of the original function? So we have to take the opposite of the original function. So we have to take the opposite of x squared plus x. And just like before, that negative gets distributed. So the x squared becomes negative, and so does the x. Does this match the original? Not by a long shot. It's completely off. So putting in a negative is not the same, does not equal the opposite of putting in a positive. So this is not odd. So if it's not odd and it's not even, then it's neither. Again, for a polynomial, and a polynomial only, a bunch of x's added together with some powers on the x's. If all the powers are even, if all the powers are odd, the function is odd. If all the powers are even, the function is even. Had this had an even power like 4, then it would have killed the negative, and it would have gone back to being the same. It would have been an even function. But let's take a look at this last one. Because I don't want you to think that, okay, I'll just look at the powers and see if they're all odd or all even. But if it's a mixture, then it's neither. Because this has a mixture of powers. The power on the top is 1, it's odd. The power on the bottom is 2, it's even. But the answer to this one is not neither. Watch what happens if we put in a negative for the x, a negative x for the x. In the numerator, we get 2 times negative x, And in the denominator, we get the quantity negative x squared plus 1, and now we need to clean it up. Upstairs, the negative is preserved. 2 times negative x is negative 2x, but downstairs, the square turns the negative positive. We get x squared plus 1. And now it's time to compare. Oops, kind of cut off the head of the 2 there. Does this match that? Almost, but no. So when we put in a negative x, it was not the same as just putting in an x, so this function is not even. But we also have to compare it to the negative of the original function. So let's set up the negative of the original function, which is just the negative of this fraction. 2x on top, x squared plus 4 on the bottom. Now it doesn't look like we could do anything with this, but there's a rule about negatives and fractions. If you've got a straight negative in a fraction, you can put it in 3 places: in the front, in the top, or in the bottom. If you really want to know why, ask me outside of class or outside of these videos and I'll let you know. But if a negative's in front of a fraction, we have the freedom to give it to the bottom, in which case it would get distributed, or give it to the top. I choose to give it to the top. Why? Because I'm trying to see if this is equal to that. You know, it just dawned on me in the previous examples I was making the wrong comparisons. So allow me to go back and I think I did. When we're comparing the first result to the second result. In this case, these were equal. Well, yeah, they were equal, so it was origin. But over here, we were comparing this to this. I think I incorrectly compared it up here. Again, I know it looks like I'm just doing a lot of alphabet soup and hand waving. But for an odd function, you compare putting in a negative with the opposite of putting in a positive. So in the second one, putting in a negative was here. The opposite of the putting in a positive was here. These are the 2 we were supposed to compare, and they weren't the same still. So we got the same results. Now, on this one, we are comparing putting in a negative, which is here, with the opposite of putting in a positive, which is here. And these match. So the function is odd. And as a consequence, it has origin symmetry. So if it's not a polynomial, you can't just use the let me check all the powers test. If it's a polynomial, yes, all powers odd, odd function. All powers even, even function. But if it's not a polynomial, that goes out the door. And by the way, the original version of this problem that had the x squared, both sides had even powers, all the powers were even, and this function actually is even, but I wanted to break the polynomial rule, and that was following it. So, as long as you know the definitions, or rather the procedure for checking odd versus even, you're okay. But both of them start the same. Put in a negative, get a new function. Compare it to the original, if they match your functions even. Compare it to the opposite of the original, if they match its odd. In the last video, we'll talk about how to kind of do these sorts of problems backwards. Not nearly as hard as it seems. In fact, it's really easy.